This is the spring 2018 final for MA 266. I'm going to be going over the questions related to midterm 2. So right off the bat here we have question 9. We're determining a suitable guess for yp of t if the method of undetermined coefficients is used on this equation right here. So even though we are looking for yp of t, the particular solution, we need to find yc of t to ensure that we don't have any overlap. So finding our characteristic equation, that's going to be r squared plus 1 is equal to 0. So our yc will have the form c1 c1 cosine t plus c2 sine t. And that's because this will give us roots of plus or minus I. And when we have two imaginary roots like that, the coefficient on those roots goes in front of the t in both of these, and we get a sine and a cosine. This is important, though, because we see that in our little guy over here, the non-homogeneous portion, I think they call it f of t, we have a sine t. And our guess originally, let's say we didn't have a sine or a cosine here, our guess would be at plus b plus ct plus d sine t plus et plus f cosine t. But there is a big problem with this in that this d sine t will this ct sine t overlaps with our t sine t up here. So in order to fix this, we're going to have to multiply our sine and cosine values or portions of the expression by an additional t. And by doing so, we get rid of that issue. And so as a result, we have our at plus b, t ct plus d cosine plus t et plus f sine. And so A is our correct answer for number 9. There we go. Skipping a couple that are either midterm 1. Yeah, all these are midterm 1 related. 13. Which of the following is a fundamental set of solutions of this fourth order homogeneous differential equation here? So we can take out our characteristic equation, which will be 4r to the 4th minus 5r squared minus 9 is equal to 0. And now that we have this characteristic equation, we will see pretty quickly if you go do the factoring. I'm actually not going to do the factoring here because with things like this, I'm actually incredibly bad at factoring it. But we'll see that we have roots. X is equal to, well, in this case it's y. Y is equal to 3 halves, negative 3 halves, I, and negative I. And as a result, the 4 solutions we're going to get is e to the 3 halves t, e to the negative 3 halves t, I, and negative I. Sorry, that's also wrong. These i's and negative i's will become cosine of t and sine of t. And notice that we don't have a duplicate. We don't have a second cosine and second sine because the pair of imaginary roots always comes with a corresponding pair of solutions. So whenever you have an I, you will always have a negative I, etc. So this is how this works out, and C should be our correct answer for 13. 14 is a little bit of a beast. So we have y1 of t as root t and y2 of t as t to the negative 1, and their solutions to this linear homogeneous differential equation given there. We're told to use variation of parameters to find the general solution of this non-homogeneous differential equation. A couple things we have to do to set things up. We have to take the Wronskian of these two solutions, which is the determinant of t to the 1/2, our first solution, and t to the -1, and then their derivatives. So 1/2 t to the -1/2 and negative t to the -2. Taking this determinant, we will get negative t to the -3/2 minus 1/2 t to the -3/2, which is equal to -3/2 t to the -3/2. I hope you can already start to appreciate how this is going to be. This is going to be a long one, so I'm going to put our Wronskian up here. -3/2 t to the -3/2, and get rid of all of this, because we're going to need all the space that we can get. Okay, next we need to figure out what function they have added on here to make things non-homogeneous. But be careful, the answer is not just 4t squared plus 4t. We need it in the case where y prime is by itself, and what I mean by that is we have to divide everything by 2t squared. So now everything is equal to 2 plus 2 t to the -1. And so that is our f of t term that we are going to be using in our equation in just a second. And actually, we are ready to solve. So we know that the general form that this equation takes is yp of t is equal to negative x1, what am I doing with x? Negative y1 of t times the integral over the Wronskian dt of y2 of t multiplied by f of t plus y2 of t times the integral, barely fit that in there, dt, I know I'm doing this in a weird order, I apologize, y1 of t, f of t. Okay, so now that we've got that in our heads, let's actually set it up and start to compute it. Usually these work out much nicer than this one does. Usually everything cancels out and you're taking the integral of like 2 dt or t dt, but you'll see very quickly we do not have that luxury here. Taking negative y1 out at the start, negative root t times, that's a nice looking integral, I gotta say, times the integral over 2 plus 2, nope, that's not there. See, I'm already getting confused. The Wronskian is there. Negative 3 over 2 t to the -3/2, and then up top we will have y2, which is t to the -1 multiplied by 2 plus 2t to the -1 dt. And our second portion of the solution will be plus t to the -1 times the integral over -3 over 2t to the -3 over 2 dt, and then root t 2 plus t to the -1. Okay, so we are ready to start solving things. This -3 over 2 in our denominator can come out as 2/3. That simplifies things a little bit. 2/3 there. And what else can we do to make our lives a little bit easier? Well, we can move this t to the -1 down to the bottom and move this t to the 3/2 up to the top. And then we'll see that this t will just get subtracted and we'll have t to the 1/2 up there. Similarly over here, we will get t to the 3 halves over here, which will combine with our root t, and we'll be left with t squared. Now we can kind of, in fact, I'm going to totally rewrite everything and then replace it. We have 2/3 root t. I'm just being especially careful that we don't lose something at some point. Root t times the integral of 2t to the 1/2 plus 2t to the negative 1/2 dt minus 2/3 t to the negative 1 integral of 2t squared plus t dt. And this is just that, so I'm going to get rid of that and shrink this guy down. Stick it right there. Let's grab our first integral, just this portion right here. We have integral of 2t to the 1/2 dt plus the integral of 2t to the negative 1/2 dt. So computing these two individually, this will be 2t to the 3 halves multiplied by 2/3, which is 4/3. Okay, we're actually a quarter done. Next we have plus 2 to the, sorry, not 2 to the 1/2, 2t to the 1/2 multiplied by 2. And okay, that's actually it for that integral. Now we have outside of everything, we have to remember we have our 2/3 root t. Oh, that's a little sloppy. And let's start computing our second half. We have minus 2/3 t to the negative 1 multiplied by the integral of 2t squared, which is 2/3 t cubed, and then plus t squared times 1/2. We are almost done. Over here we will get 8/9 t squared, and 8/3 t. Moving over to our second half, we will get negative 4/9 t squared and negative 2/6, so negative 1/3 t. And I just said minus 1/3 here, and paused the video and realized that I dropped a 2 all the way back here where we had distributed a 2 out to t squared plus 1. So with that in mind, this integral here will actually give us t squared, so this will be minus 2/3, and we get our correct answer, which is 4/9 t squared plus 2t, because we'll get 6/3, plus c1 root t plus c2 t to the negative 1, because remember, we're actually computing y of t, which is yc that we already knew, plus the yp that we just found. This is the most brutal variation of parameters question I've ever seen, that at least them give on an exam, and so I really hope that we don't have to do this kind of thing ever again. 14 is A, although I will have to do it one more time when I record my final videos. Oh God. 16, the solution to this initial value problem here. Okay, so I'm relatively new to Laplace. We'll see how this goes. We are going to need to write down a couple of facts. Y double prime, the Laplace, of y double prime is equal to, okay, I'm just going to preface this. I'm not sure if it's a good or bad habit. I've been using alpha instead of s for my Laplace transforms, and I hope you'll see why soon, because my s's look exactly like my 5s. I'm not even sure which one of these is a 5 and which one is an s. So now I also really like drawing alphas. So we have alpha squared y of alpha minus y0 of alpha minus y prime of 0. And secondly, we also know that the Laplace of y prime is just alpha y of alpha minus y at 0. And using these facts, we can rewrite this as in Laplace form, in the S domain or the alpha domain, whatever you want to term it. So this y double prime will become alpha squared y alpha minus y0 alpha, which is -1 times -1, so plus alpha, minus y prime of 0, so minus 4. And then our 4y will just become 4y in the alpha space. And then this g of t, I'm just going to write down as the Laplace of g of t. And okay, we are almost ready to actually start the whole solving thing. I'm going to subtract this alpha to the other side and add the 4 to the other side, and then factor out y alpha from the left side. So we'll have y alpha multiplied by the quantity alpha squared plus 4 is equal to the Laplace of g of t plus 4 minus alpha. And of course, we're just going to divide out this term here. We're left with y alpha is the Laplace of g of t divided by alpha squared plus 4. And then we have 4 over alpha squared plus 4 minus alpha over alpha squared plus 4. And quickly, we know that these two terms are going to be easy peasy to solve for. This guy right here is just I need some place to put this. We have y of t. We know that one of the components of y of t composed of this thing is 2 sine 2t. And where am I getting that from? Well, we know that the Laplace of a over alpha squared plus a squared, we know that the inverse Laplace of this is sine at. And since we have a 4 on top, we can factor a 2 out from that. We'll have 2 over alpha squared plus 4. That's just this case for a equals 2, and we're left with a 2 multiplied on the outside. I'll actually leave that up here because cosine is very similar. That's just going to be alpha over alpha squared plus a squared is cosine at. And so in our case, right here, we have an alpha over alpha squared plus 4, so we can subtract a cosine of 2t like that. And now all we have left to deal with, everything that's still sitting in our alpha space that we haven't dealt with, is the Laplace of g of t over alpha squared plus 4. And hopefully I can jog my own memory on this by pulling up one of our tables that we get for these exams. So to help us along the way, we're going to split this up as the Laplace of g of t multiplied by 1 over alpha squared plus 4. And we have this nice rule here, if I can find it, yeah, that says that the inverse Laplace of some function f of s times some function g of s is just the integral from 0 to t of the function that when you take the Laplace of it, you get f of s, where all t's are replaced with t minus tau multiplied by your still unknown and arbitrary function g, in this case g of tau. So for us, what this means is that we can express this as the integral of g of t, because the inverse Laplace of the Laplace of g of t will just give us g of t. And then the function that we would take the Laplace of to get this guy. And that would be, let's see, if we write this as 1/2 times 2 over alpha squared plus 4, well, the Laplace, or the inverse Laplace of this will be, just as we saw earlier, the Laplace of a over alpha squared plus a squared is just sine at, sine 2t. So we can take this guy and replace all of our t's with t minus tau. So this is 1/2 sine 2t minus, bad tau, come on, t minus tau. This is a g of tau, if we want to be clear, integral from 0 to t dt. And this, okay, I'm gonna need more space. I'm gonna go use the next question's space. This right here is our solution, and they factor out the 1/2. But we see we have 1/2 integral from 0 to t of g of tau sine 2t minus tau d tau plus 2 sine 2t minus cosine of 2t. So D is our answer for problem 16. There's something about these Laplace transforms that are noticeably more satisfying than a lot of the stuff that we've been doing before. I kind of like it. Okay, let's find the Laplace transform of this thing. What is this thing? This thing is a special kind of case of a unit step function. So we know that u1 of t, this is a unit step function that activates when t equals 1. We can graph this out for all t from 0 up to 1. Our function is 0, and then at t equals 1, our function will jump up to t equals 1. So it's discontinuous there, but all that we need for the Laplace transform of this function to be defined is that the function itself is piecewise continuous, and in this case it is. There's a continuous piece. There's a continuous piece. There are discontinuities between the pieces, but overall you can take enough snippets of it to form to be continuous over everything. That doesn't actually make sense. I hope you understand what I mean. So we want our function to be equal to t from 0 to 1. I'll actually just bring this graph right back. So equal to t from 0 to 1, and then equal to 1 elsewhere. So how can we do this with step functions? Well, we want some step function to be active from 0 to 1, and then to deactivate there. So I will write that as 1 minus u1 of t multiplied by t. And I hope you can see what this is really, and I need another parentheses, what this is really doing. So this is saying, well, for, let's say, t is equal to 0.5, u1 of t is going to be equal to 0. So this whole thing will evaluate to t. But as soon as t hits 1, this thing is going to activate. We will have 1 minus 1, and so our t will no longer be controlling things. And now all we have to do is add a u1 of t into the mix to turn on when this one, when this expression, this whole section turns off, so that we continue along the desired path. So now that we kind of get what's going on conceptually, let's see if we can rearrange what we have here in our f of t to see if we can make some sense of how we're going to Laplace this guy. So we can expand things to t minus t u1 of t plus u1 of t. Let's factor a u1 of t out, we will have t plus u1 of t, that looks like an f, t plus u1 of t multiplied by t minus 1, and in order to do that I'll have to, factor a negative 1 out here. So this is still our f of t, and this is something, believe it or not, that we know how to deal with. We'll see rule 13 up here, or property 13 of the Laplace transform, says that uc of t multiplied by some function of t where all of the t's are replaced with t minus c's, which we see that we satisfy this condition. We have u of c where c is 1, and then we're subtracting 1 from all of our t's. That this, when we apply the Laplace transform, is just e to the negative cs, where c is that original constant, u of c, multiplied by the Laplace transform of the function f. So working on this, we will see that the Laplace transform of, remember, I'm just dealing with this section right now. We'll get to the t. We'll get to the t in a second. This will just give us e to the negative, not e to the negative t, e to the negative alpha for c is equal to 1. And then we want the Laplace transform of t minus 1. And the Laplace transform of this function, f of t minus c, well, that's actually just going to be equal to the Laplace transform of the function f of t, because remember, the Laplace of f of t is what becomes capital F of s. So we ignore that negative 1 and we just take the Laplace of t. The Laplace of t is 1 over alpha squared. So we've dealt with that entire section. We have to remember to add our negative sign, and we've already figured out what the Laplace transform of our t is. This is just going to add a 1 over alpha squared, and so we can rewrite this as 1 minus e to the negative alpha over alpha squared. And that gives us option B. So 17 should be B, and it is. Okay, we can get rid of our Laplace transforms, I'm pretty sure, forever for the rest of this exam, and we are trying to identify the phase portrait of this system. So this is all to do with the signs or the kind of data types, whether complex or real or purely imaginary, of the eigenvalues of this matrix A here. So we will be solving negative 2 minus lambda times negative 4 minus lambda minus 3 is equal to 0. This will give us lambda squared plus 6 lambda plus 8 minus 3 is equal to 0, or lambda squared plus 6 lambda, the cat is jumping off the bed, plus 5 is equal to 0. This will factor to lambda plus 5, lambda plus 1. And so we see that both of our values for lambda, negative 5, negative 1, are negative, and they are both real. And so if we draw our phase plane, over here just a basic x1, x2 plot, we will see that because both of our eigenvalues are real and negative, we will have radial flow into our origin. Some of these arrows are looking a little healthier than others. And what this means is we can identify this behavior pretty easily. We have an asymptotically stable node. When we approach t is equal to infinity, any starting point will approach the origin. You can kind of think of it as a depression in a trampoline or some other surface like that. Things over time will decay into that center there. Whereas if these were positive, we would have an asymptotically unstable node where things would be forced away radially as time goes on. But in this case, we have an asymptotically stable node, and so 18 is A. I'm pretty sure that some of our terminology for this has actually changed because this is the 2018 exam, and we've changed textbooks since. You would expect them to call this, I think, an improper source node or something, no, sink. I'm not actually sure, which is too bad because that's the one we're going to be tested on. We'll see how that goes. 19, we're finding the general solution to this thing right here, and we should already be expecting to find multiple eigenvalues, or in this case, a single eigenvalue with a multiplicity of 2. And you could save some time if you really wanted to on these kinds of questions, and notice that they're using a -6 in all, literally all of their exponents. So you know that -6 is the eigenvalue that we're going to find, but we are going to find it manually, but I'll take a couple shortcuts. So we will end up with the characteristic equation, lambda squared plus 12 lambda plus 36 plus 32 plus 4, which is 36, is equal to 0. This will factor to lambda plus 6, lambda plus 6. So there is our lambda equals -6 with a multiplicity of 2. So for lambda equals 6, a minus 6i is going to be a minus -6i, so a plus 6i, 2, -2, -1, 4. Come on, cat. That will simplify down to 1, 2, 0, 0, and we can get the eigenvector. -2, 1 out of that, like so. Next, we are going to need to find a generalized eigenvector because we can't just reuse the same eigenvector with a t added onto it. And the way we find that generalized eigenvector is taking a minus lambda I, so 2, 4, -1, -2, and smacking the eigenvector that we found for that on here and making a nice augmented matrix, -2, 1. So we can simplify this down to, 1, 2, -1, 1, 2, -1, 0 out that row. And we'll see that if we solve this, we will get the same eigenvector here, but with a constant term. And this constant portion of our eigenvector that we'll find is our generalized eigenvector. So we have -1, 0 as that eigenvector. Now, in fact, we are ready to solve or to write down our full equation. So one kind of sneaky thing that they've done here is flip all of the values that we found in our vectors. So our -2 1s became a 2 -1, and our -1 0 became a 1 0. And they can rationalize that by just saying that the C2 and the C1 could be negative to compensate, and that would result in the same equation. But in the end, E is our correct answer. Remember that when we have a generalized eigenvector, our solution is going to look like C1 V1 e to the lambda t plus C2 V1 t plus V2, where V2 is our generalized eigenvector, e to the lambda t. So E for 19 is correct. 20, we have a 2 by 2 matrix with complex eigenvalues, -2 plus or minus I, and an eigenvector corresponding to that to one of our eigenvalues, the plus side of the conjugate. And we're told very nicely, in fact, that this non-homogeneous system up here has a solution given there. And we are trying to find the general solution to this whole system. And so all we need in order to solve for this, to solve for the components that will be attached to C1 and C2 for our x of C, or characteristic equation, is to take v1 e to the lambda t, so that will be 1, negative 1 minus I v1 times e to the lambda t. So that will be e to the negative 2t times, and I'm just expanding it a little bit, e to the I t. We can replace e to the it with cosine t plus I sine t, and we'll need to separate this entire thing out into the real and complex vectors that we're going to get out of this. So our real vector is going to have cosine t on top, because that's the only, one of these two that when multiplied by our top, any component of our top vector, vector entry will give us a real value. So there's our cosine t, and on the bottom we will have a minus cosine t and a sine t. And we are getting that because this I times negative I will give us a positive 1. And so this is e to the negative 2t, and then we'll need our I, our imaginary vector, which will come from I sine t and minus I cosine t, so minus cosine t and minus I sine t, e to the negative 2t. And now we can drop this negative 1, add a c1 and a c2, and make sure to include our xp, and we are done. Let's just match this up with one of the equations up there, and it looks like B matches perfectly. Okay, thanks for sitting through this, especially that variation of parameters one. That was a real pain. Hope you're having a good day.